For centuries, extraction meant patience. Plant material submerged in solvent, left to soak for hours, sometimes days. Compounds slowly diffusing out, cell by cell. It works, but it's passive. The plant gives up its chemistry on its own terms. But what if you could force the issue? What if instead of waiting, you could break those barriers open mechanically? Enter sonication, ultrasonic extraction. The problem? Most of what you want is locked inside. Rigid cell walls, tough fungal chitin. These structures don't dissolve easily. They protect their contents, and simple soaking can only extract what seeps through naturally. An ultrasonic transducer vibrates at frequencies beyond human hearing, 20,000 cycles per second or more. These vibrations travel through the liquid as pressure waves, alternating between compression and expansion. In the low pressure phase, the liquid is stretched apart at the molecular level, and in those tiny voids, microscopic bubbles begin to form. These aren't ordinary bubbles, they're cavitation nuclei, unstable pockets of vapor that grow rapidly during each low-pressure cycle. Dissolved gases rush in, the bubble swells. For a few microseconds, it exists in a fragile, expanding state. Then, the high-pressure phase hits, and everything changes. The bubble can't sustain itself against the crushing force. It collapses, not slowly, but violently. The walls rush inward at hundreds of meters per second. The implosion is so rapid, so intense, that it generates temperatures hotter than the surface of the sun, concentrated in a space smaller than a human hair. At the moment of collapse, something remarkable happens. The asymmetric implosion generates a microjet, a tiny spear of liquid moving at tremendous speed, launched outward from the collapse point. Shockwaves radiate through the surrounding fluid. This is acoustic cavitation, sound waves transformed into mechanical violence. These microjets are the key. They strike cell walls with enough force to punch through cellulose fibers and fungal chitin, structures that would resist chemical attack for hours. Each impact creates ruptures. Cracks propagate outward, and through those breaches, the compounds inside begin to flow free. Alkaloids, terpenes, flavonoids, pigments. The chemistry that was locked away now diffuses rapidly into the surrounding solvent. What would take hours of passive soaking happens in minutes. The extraction is faster, more complete, and more efficient. Pull back from the microscopic chaos, and you see the full picture. Thousands of cavitation events happening every second. Thousands of microjets, a continuous process of controlled destruction and liberation, all driven by sound waves passing through liquid. That's acoustic cavitation. Not chemistry, not heat, pure mechanical force, harnessed at the microscopic scale to unlock what nature spent millions of years protecting. The future of extraction isn't about waiting. It's about breaking through. Ultrasonic waves create cavitation, millions of microscopic bubbles forming and collapsing with incredible force, breaking open cell walls to release valuable compounds. When it comes to ultrasonic extraction, power isn't everything. What really matters is control. But all that energy comes at a cost. Cavitation generates intense heat. Uncontrolled sonication can push solvent temperatures above 60 degrees Celsius in just minutes, well beyond the thermal tolerance of most bioactive compounds. And heat destroys what matters most: delicate terpenes, volatile alkaloids, the compounds you're trying to protect. Monoterpenes begin degrading at just 40 degrees Celsius. Flavonoids lose potency above 50 degrees Celsius. And heat-sensitive alkaloids, they're often the first to go. So how do you fight back? Jacketed beakers circulate cooling fluid around your vessel, pulling heat away in real time. The cooling jacket creates a thermal barrier. Cold fluid continuously absorbs heat from your extraction vessel, maintaining precise temperature control throughout the process. And pulsed sonication cycles the ultrasound on and off, letting your solvent cool between bursts. The best results come from combining both strategies: jacketed cooling for continuous heat removal, plus pulsed sonication to prevent thermal spikes. A typical duty cycle might run 5 seconds on, 10 seconds off, giving your solvent time to dissipate heat while still delivering consistent cavitation energy. No complex hardware needed, just smart thermal control, protecting every extract. Smart thermal management isn't optional. It's the difference between a good extract and a great one. The result? Higher yields, better purity, and extracts that preserve the full spectrum of compounds nature intended. The horn is your energy transducer, the part that actually delivers ultrasonic power into your sample. Each horn is precision engineered with specific geometry, the taper, the length, the tip diameter, all calibrated to deliver exact acoustic performance. Microtips focus high amplitude into a single concentrated point, perfect for small batches between 1 and 50 milliliters. When you're working with rare samples, expensive reagents, or limited material, every microliter counts. That concentrated energy creates intense, localized cavitation, microscopic bubbles imploding with enormous force, perfect for lysing cells or dispersing nanoparticles. Standard probes spread energy across larger volumes. The choice comes down to your application: pinpoint intensity versus distributed power. Standard probes deliver consistent energy across 50 to several hundred milliliters, ideal for routine sample preparation and medium-scale extractions. And flow-through cells? They handle industrial-scale continuous processing, pumping material through an intense sonic field non-stop. Microtips, standard probes, flow-through cells, each tool in your ultrasonic arsenal engineered for its specific mission. Scale up to thousands of liters per hour. Continuous processing means no batch limits, no downtime, just relentless sonic energy. Inside the chamber, material passes directly through the most intense cavitation zone, maximum energy transfer with every pass. Ultrasonic extraction is powerful, but only if you match your equipment to your sample size. Get it wrong, and you'll either waste energy or destroy your material. You can't use the same wattage for 10 milliliters as you would for a full liter. The reason comes down to power density, the amount of energy concentrated per unit volume. Too much intensity in a small sample creates hotspots. Too little in a large batch leaves material unprocessed. For microscale batches, 50 to 150 watts with a microtip is enough. Mid-scale needs 200 to 500 watts. Large scale, 750 and above. Heat is your hidden enemy. Continuous sonication builds up temperature fast, which can degrade heat-sensitive compounds. The solution? Pulse mode. Run 5 seconds on, 5 seconds off. Or use an ice bath to keep things cool. Then there's amplitude, how far the probe tip actually moves. Higher amplitude means more aggressive cavitation. Start at 20 to 30% for delicate samples. Push to 50% or higher for tough plant material or high viscosity liquids. But wattage is only half the equation. Your probe tip diameter matters just as much. Microtips concentrate energy into a tiny point, perfect for small volumes. Standard tips spread that energy across a wider area for larger batches. Above. But here's the thing. More watts doesn't mean better quality. The opposite problem? Underpowering. If your wattage is too low for the volume, you'll see weak cavitation, incomplete extraction, and wasted time. The liquid barely moves. It means managing power density relative to your volume. Remember, match your wattage to your volume. Choose the right probe tip. Control your amplitude. Manage your heat. Do all four, and you'll extract more, faster, with less waste. When you hit the sweet spot, you'll know it. Steady, controlled cavitation, a slight haze of microbubbles, consistent temperature, and most importantly, maximum yield without degradation. Here's a quick rule of thumb. Aim for 20 to 50 watts per 100 milliliters for most applications. A 500 milliliter batch? That's 100 to 250 watts. Scale proportionally from there.